Okay, the section that we are about to start now deals with the detection of cosmic rays. When I say detection of cosmic rays, I implicitly mean direct detection, because contrary to indirect detection, we really detect the cosmic ray particles before it interacts with Earth's atmosphere. Now, I've collected some of the main features of our detector. That is, what the required performances are and what we are interested to measure. So the first thing that we are interested to measure is the particle's identification. That is, we would like to know, is it a heavy nucleus, is it a light nucleus? And in the best of all worlds, we would be able to distinguish individual species and even distinguish between isotopes. The second thing that we are interested to measure is the energy, to measure, for example, the energy spectrum, either of a single species or of the all-particle spectrum. The third component we would like to know is the charge sign. So we would like to be interested to know whether it's a positive or negatively charged particle. Combined with properties like the mass of the particle, we can therefore distinguish positrons from protons, and we would be able to measure also antiprotons, and we would be able to measure antiparticles even of heavier species, like, for example, antideuteron, antilithium, etc. Finally, the direction is of interest, not so much for charged cosmic rays, because charged cosmic rays tend to be deflected in the magnetic field of our galaxy, but for example, not charged component of the cosmic rays, that is photons, directional information is very crucial. But even for the charged cosmic rays, it is interesting to measure the direction, as it would allow us, for example, to measure the charge-dependent deflection around the moon, which casts a shadow on cosmic rays. So this is something there, a moderate type of resolution is necessary. I've listed some of the requirements on these particular measurements. That is, for example, for the charge separation, we would like to be able to measure the charge with an accuracy less than unity. For the energy resolution, we do not require very good energy resolution, as the features are usually broader in energy, and therefore high resolution is not necessary. But still, we would be interested to measure the energy with a resolution better than unity in terms of energy resolution over the energies, that is the relative energy resolution. There is a second part which deals with the energy resolution, which is not the statistical uncertainty of the measurement of each individual energy of a particle, but that's the systematic uncertainty with which our detector reconstructs a given energy. And that systematic uncertainty is rather important, as it is difficult to calibrate, first of all, and for steeply falling spectra, any shift of the energy will shift the power law to a high energy or to a lower energy, and therefore the flux will change. That for very strongly falling power laws like the cosmic ray spectrum this is an effect which is quite important in terms of the flux measurement in turn. The measurement of charge sign, combination with a good rejection between different particle species of the order of 10 to the minus 4 to 10 to the minus 7 is required in order to, for example, measure the rare positrons against the large foreground of protons. And finally, it is important to note that direct detection techniques rely upon having a detector flown either on top of the atmosphere or even above the atmosphere. And that's something where you need to have a sufficiently compact and sufficiently lightweight detector to be able to be carried up by a stratospheric balloon or brought up to an Earth orbit with a rocket. There's many different components that make up a cosmic ray detector, and in the best of all worlds, you would combine several different components to make independent measurements of the same quantities. However, there's basically two detector components which you will find universally in all kinds of detectors. In various manifestations, of course, but in principle, you would be interested to measure the track of the charged particle as it passes through the detector. That's done with something we usually would call a tracker. And the second component would be a calorimeter, which is a device which measures, broadly speaking, the energy of the incoming particle. Additional components are, of course, often used This could be, for example, hodoscope, time of flight measurements, and so on and so forth. But they are usually based upon the same principles. And actually, sometimes even combinations of these things can be done in a way that one detector would be able to measure the track and even to some extent the momentum, which is for low energy particles and energy measurement. And you could also have a calorimeter, which has some spatial resolution and could act as a tracker. Now, the following discussion is heavily relying upon a very good book by Hermann Kolanowski, which is called Particle Detectors. In the 6th edition, this book appeared just last year. And section 3 outlines some of these points which I want to make here. So let's start with a very brief discussion on the underlying interaction principles, because every detection requires an underlying interaction. So there's no detection without interaction. And luckily, most of the detector components we can understand by looking at one single type of interaction. We will have to introduce 2 more later on for the calorimeter, but for the tracker, for example, it's perfectly sufficient to just discuss ionization losses. And ionization losses are also something which can be dealt with rather simple way in the sense that you want to calculate it. If you want to go into more details, it gets increasingly more complicated, but the complications come from matter-related effects. But the principle of, let's say, microscopic physics which is involved is that a charged nucleus, for example, of charge number like Z, I call it here, of mass capital M, Lorentz factor gamma, and velocity beta in terms of V velocity over C, impinges on a medium where you have nuclei and electrons combined in a normal way. So you have neutral atoms present, and the nucleus that comes in with a high energy basically will do elastic scattering on the electrons in the bound state. And this can be described in terms of interaction, first of all, of 2 point-like particles, and also in terms of something which doesn't have spin, which is not completely accurate, but we can modify the cross-section, and we will find ourselves confronted with the Rutherford cross-section, which is well known, which is given right here. So that's Rutherford cross-section, and the Q is the 4 momentum transfer from the initial state to the final state electron. So what we're looking at essentially in initial state is an electron which is broadly speaking at rest. That is in the bound state, and its energy is dominated by the rest mass. There's of course a little bit of binding energy involved, but this is negligible. In the final state, this electron will be upscattered, and it will obtain kinetic energy T on top of its rest mass, and it will be free, unbound. That's why it's called ionization. And then we can re-express this 4 momentum difference squared Q squared to be in a simple approximation, which is good enough in our case, 2mec squared times T. And this way we can rewrite the Rutherford cross-section from T sigma over dq squared into something where we basically now deal with the cross-section per kinetic energy gain. And then we end up with this term here. And then we finally have to consider that, of course, we're dealing with an electron which has a spin. And so we have to modify the Rutherford cross-section with to become the mod cross-section. So we have to multiply with this term here, which is 1 minus beta squared T over T max. And then we finally can calculate the average energy loss. And that is given by the integral over the energy T min to T max. So that's the minimum energy that you can impinge on the electron up to the maximum energy. And then you just integrate the cross-section times the energy times the number density of electrons. In this case, we however, ignore all kinds of shielding effects. This come into the game a little bit later. But we get the so-called Bethe-Bloch equation in first order. And then the Bethe-Bloch equation basically has this kind of shape, which you see here. So it has a term here which goes with 1 over beta squared, and it goes with z squared over here. And here this is the number of electrons in the medium, so this depends upon the density of the medium. And you've got a logarithmic term coming from the integration, and the beta squared term comes from simply this this mod expansion. Now, kinematics, I'm going to skip over here. You can calculate that yourself, but in the end you have a general term for T max, which you can get, and asymptotically T max becomes gamma mc squared. So you can get the full energy over to the electron. The minimum energy is a little bit more complicated to deal with because you have to deal with the excitation levels, the energy levels of the underlying atom. And there's an approximation that's usually involved. So basically you calculate something which is called the average excitation energy, called capital I, and that relates to the oscillator strength of individual level Fk and the energy of each bound state level Ek. And then T min is given by I squared over beta squared MEC squared. And there's a factor of 1/2 also involved here. And here's a plot which shows this dependence of this average value of I over the z value. So this is I over z here, and often enough it's just simply approximated by this continuous curve. But you see there's some shell structures which are usually ignored in this whole thing. So the full energy loss term you'll find here in this equation, which is something you can find in any textbook. It's rewritten in a slight way and also contains now the corrections which are needed for both the high energy end, where shielding effects and the medium have to be taken into account. And for the low energy part, you have another correction which deals with the atomic structure. So what happens at high energies? Because of the increasing relativistic effect, the electric field, which you have to consider when you do the interaction in the medium, basically leads to that the electric field in the transversal part is increased through the boosting. And that leads to an more increasing scattering effect on electrons, which are even further away. And then there is a saturation effect, which comes from the fact that the medium basically starts to shield the electric field of the incoming particle. And that is something which is taken into account with a parametrization. And so the function, if you plot it now, plotted here now is dE over dx, and you divide out this term rho here, which you got. So if you divide that out, then you basically get the energy loss per path length times the density, and that's something we call the column density. That's usually given in units of grams per square centimeters. So this is now units MeV per grams per square centimeters. And so you find the 1 over beta term, which is essentially the part which we derived in our Bethe-Bloch part. And then at high energies, you find the delta correction, taking into account that there's a rise. And then there's an additional shielding effect. So then you end up with this solid line, which is showing a smaller energy dependence than just the one which basically does not take into account the shielding. So the shielding effect is quite substantial, but it's not treated here. What you can conclude from this is that ionization energy losses are largely energy independent. So keep in mind the X scale is in logarithmic scale, so it goes over several orders of magnitude. And the value of the energy loss changes by less than a factor of 2 when you go over that large energy range here. So that makes it almost energy independent. So by measuring the ionization, for example, you are not able to measure the energy of the particle. However, what you can measure is that this is now for a charge z equals 1 particle. Now, if you would plot the same thing for a charge z equals 2, the ionization losses would be 4-fold that much. And that's something which is critical and crucial for measuring the charge number. Now, you notice also that there's a minimum value here. That's the so-called minimum ionizing part. And then this gradual increase. So this shape of this curve does not really depend a lot on the part on particular target that you're dealing with. And I give here on the right some of the numbers in a table for various different materials as a target: carbon to lead, and also some gas, and also some composite material. And you see that, for example, even though the density changes widely, the minimum value of the ionization losses, which is given in the last but one column, is pretty much constant in range between 1.5 and 2 MeV per grams per square centimeters. The bottom table relates to the correction function delta, which I gave before. So delta is a function of beta gamma is given here, and it depends upon a material constant zeta. And zeta is given over here, so zeta 0, zeta 1, and also this CD, which is used here. So zeta is this part of this value, which is zeta is defined as, this I should better write out here. So this is the zeta function. That's simply log 10 beta times gamma. And CD is a constant which relates to the plasma frequency, basically the electron density and the medium. And for the asymptotic value of a very large value of gamma, this delta function goes towards something which still rises to logarithm beta gamma. Now going further, let's apply this. And before we apply this, it should be really clear that you can basically write down the energy losses as a simple scaling law, where the energy loss per path length just depends upon zeta squared and some function of beta. Okay, so that does not depend upon the material. So you're basically free to choose what material you want. It doesn't really matter. Now, let's think about the simplest way that you can apply these ionization losses. So of course you can detect a particle passing through a detector if you are able to measure the ionization or the energy loss there. So think about several MeVs of energy deposited, for example, in your detector, and if you are able to detect that, you know that the particle passed through, because this is a lot of energy that you deposit. It's still little with respect to the overall energy budget. If you think about the relativistic electron with several GeV passing through your detector, it'll lose only several MeVs passing through your typical detector geometry, and therefore it does not get stuck directly. So you could have two layers of a detector material, which is positional dependent, and then you would be able to reconstruct the 2 points of interaction where the particle passed through the first layer and then through the second layer, and you could draw a line between these two, and then you would know where the particle came from and which way it went. You could also be able to measure, for example, the time between the two passages, so that you would be able to reconstruct also the velocity. And that's actually something which is often used for small energy particles. For ultra-relativistic particles, this is not working anymore, because at gammas of, let's say, several tens or 100, you would have to have a very good resolution to measure any velocity difference anymore. And that's usually not feasible. So this works for, small and mildly relativistic particles, time of flight. But you can still reconstruct the track by saying, these two positions were hit. You would still not be able necessarily to measure which direction the particle came from, when it came from the bottom, but you would still be able to measure the track of the particle. So one way of making a spatial resolvable detector, which is used commonly these days, is, for example, a silicon strip detector that is competing with other ways of measuring it, which usually rely upon scintillator detectors, which are somehow separated in various little chunks where you can read out individual channels. The advantage of a silicon strip detector is you can make the resolution very big, very good, and the detector is working also in a very efficient way. So here, this is basically giving an idea. So assuming you have some wafer that's typically 300 micron thick, and that is made out of N-type silicon, and then you could have basically a layer of N-doped silicon on the one side, and you would have small readout strips which have P-doped silicon on the other side. So this works like a junction, silicon junction, with all the physics behind it that you know from solid state. The basic idea is that you would apply an electric field between the two electrodes. So you would have aluminum electrodes, basically just a surface electrode on the one side of the strip detector. And on the other side, you would have segmented, for example, strips of aluminum. And so a charged particle passing through would produce electron hole pairs, because you would have ionization energy available to lift an electron out of the ground state or ground band to the conductive band, and you would create a hole and an electron pair, and they would then move in the outer electric field respectively up and down. And you would then, for example, at the electrodes up here, you would measure the charge that's accumulated, and you would amplify this, and then you would be able to detect that there was a particle passing through. Now, the typical number of pairs which are produced, you can estimate by simply assuming you have a 300 micrometer silicon that the particle passes through, with of the order of 300 electron volts per micrometer in silicon. That's the typical loss per path length. You would end up, given that each electron hole pair has at least 3.6 electron volt required, you would get, roughly speaking, up to 2,400 pairs. You could get less, of course, simply given that ionization losses will not always just deposit 3.6 electron volts. You would basically also produce some electrons with some kinetic energy in the conductive band. But this is roughly just an estimate, and that corresponds to about 4 femtocoulomb that you can collect, amplify, and measure. Now, the realization of such a thing could look like this. So this is a silicon wafer. You see that there's some structure on it, which are the electrodes. And there's, for each of the strips, you basically have a readout channel, which is then fed into your data acquisition, which basically allows you to measure the particle passing through. The spatial resolution is limited by how big the pitch is, that is the separation between the strips. And with a 5 to 50 micron, this is basically as good as you can get. Often enough, it's like 60 or even 50 or 100 micron. But this would be sort of the best resolution that you can achieve. And this would then relate actually to a better resolution than the 15 micron pitch, simply by given that even in the worst case that you would detect only on one of the strips any kind of signal, you would still be able to, on average, resolve the position, assuming that they are uniformly distributed even between the two strips, by 1 over square root 12. That's an interesting calculation to do maybe at home. Now, there's additionally something which should be considered for a moment, is that, of course, what we're looking at are the average energy lost in ionization per path length. However, if you look carefully, of course, that's a statistical quantity. And the distribution of energy losses, that is where we just basically looked at the average value before, is something which is necessary to consider when you in the end want to know how good is my charge resolution. Because as I said, you will have then sort of bands of energy losses which relate to charge 1, charge 2, and so on and so forth. And how broad is that? Independent of how good your readout works in the end, we were seeing that basically a particle passes through, you get something like 2,400 electron hole pairs. So you could measure that quite accurately to a precision of less than 1%. Or a few percent accuracy, how much charges, how much ionization losses are there. However, you're limited by the fact that intrinsically the ionization losses is a statistical process, so you will have a distribution. And that distribution was derived by Landau and Bethe-Bloch some time ago as an analytical solution. And I don't want to go into the details here, but there's an interesting feature, that is, if you have very few energy scattering effects taking place, you will have an asymmetric distribution that's shown here to the right. So this is corresponding to that in each individual scattering case, you have less than the maximum possible energy lost. And then you have a tail towards large energy loss, let's say large energy losses. If you consider, let's say, a medium where you have many scattering taking place, and so that the overall energy lost is larger than the one that you could maximally lose in a single scattering event. So you'll have ultimately many scattering events. Then basically, according to the large central limit theorem, you start getting a Gaussian regime. But still, it is then still something which has an intrinsic scatter which you have to take into account.